Hello, I'm Seema and welcome to part 8 of the chapter Chemical Bonding and Molecular Structure. Moving ahead with our discussion about the bond parameters, we have already discussed bond length, bond angle and bond enthalpy in the previous two videos. Let us now deal with bond order. Bond order is nothing but the number of bonds or the number of shared pair of electrons between two atoms, right? Now, hydrogen and hydrogen share one pair of electrons, so they have a single covalent bond. Therefore, hydrogen has a bond order of 1. A hydrogen molecule has a bond order of 1. Oxygen molecule, O2, has two pairs of electrons that are shared. It has a double covalent bond. Therefore, it has a bond order of 2. And nitrogen, which has 5 electrons in its outermost shell, both the nitrogens, they share 3 pairs of electrons forming a triple bond among themselves, and therefore a nitrogen molecule has a bond order of 3. So bond order is basically nothing but the number of shared pair of electrons or the number of bonds shared between atoms. Isoelectronic molecules, and isoelectronic means molecules which have the same number of electrons or which show the same kind of bond order. They usually have the same bond order. For example, fluorine and fluorine. Each fluorine has 7 electrons in its outermost shell. And in order to complete the octet, it needs to form one bond. Therefore, the fluorine molecule is formed by sharing one pair of electrons between the two fluorines, resulting in a single bond, and hence the bond order is 1. So 9 plus 9 electrons that they have, the total number of electrons, or rather I should say if we count only the valence electrons, 7 plus 7 electrons would be 14. And oxygen has 6 electrons in its outermost shell, and the other oxygen also has 6 electrons in its outermost shell, but O2, 2 negative ion, would have 2 extra electrons, so 6 plus 6 is 12 plus 2, 14, which becomes equal to the number of electrons in fluorine. So these two are isoelectronic species. So O and O in O2, 2 negative would also have the same bond order, that is the bond order of 1. It's very easy to understand it logically. In order to complete the octet, each oxygen already has 6. It needs 2 more electrons. So if we assume that these 2 electrons that have been gained, one goes to each oxygen, so now the deficiency that lies is of 1 electron each, and therefore they should share one pair of electrons, resulting in the formation of one bond, and hence the bond order is 1. Oxygen molecule, as I told you, would have a bond order of 2 because both the oxygens have 6 electrons each, and in order to complete the octet they need 2 electrons. They do so by sharing 2 pairs of electrons, and the bond order is 2. Nitrogen, 3. And if you see these isoelectronic species again, C triple bond O and N triple bond O positive. NO positive ion, C triple bond O. These are isoelectronic and they also show the same bond order, that is the bond order of 3. Now we find that as the bond order increases, this is 1, 2, 3. In the previous video, when I discussed the bond enthalpies, I told you that the bond enthalpy of hydrogen is 435.8 kilojoules per mole. The bond enthalpy is the amount of energy which is required to break 1 mole of bonds between 1 mole of the molecules of that substance. So the bond enthalpy of oxygen, or the enthalpy of atomization of oxygen, is 498, and that of N triple bond N is 946 kilojoules per mole. Do you know that nitrogen molecule is among one of the molecules which has the highest enthalpy of atomization because of the bond order 3? And there cannot exist more than 3 bonds between 2 atoms. Therefore, you can have bond orders of 1, 2 and 3. Because sharing 4 pairs of electrons between 2 atoms would have too many electrons between the two, leading to repulsion. And therefore, this is the maximum bond order that you could have. So this was the 4th bond parameter, which is bond order. Let us now come to the fifth parameter, that is resonance. We have observed that when we draw the Lewis structures of certain molecules, we can draw more than one Lewis structure, and none of those structures actually completely explains the molecules. But you can have certain forms, you can draw certain Lewis structures, more than one Lewis structures for a molecule. An example is ozone. If you take an ozone molecule, you see these are two Lewis structures that I can make. You have 3 oxygen atoms, and we know it's not a triangle. That's not how it is. We have these 3 oxygens where one of the oxygens has a single bond and one of them has a double bond. So if you have 3 oxygens in one structure, you can have the double bond on the right hand side of oxygen, and in one structure you could have the double bond on the left hand side. Now, what we see, if you had one single and one double bond between the 3 oxygens, then the bond length of a single bond should be 148 picometers. That is the bond length between 2 oxygen atoms. And if there was a double bond between 2 oxygens, then the bond length should be 121 picometers. As I told you, that as the bond order increases, the bond length, the enthalpy of atomization increases and the bond length decreases. Why does the bond length decrease as the bond order increases? The bond length decreases because I told you in the previous video, let us assume bonds to be friendships. When there is one bond, the length is whatever. As you have 2 bonds, the atoms come closer. 3 bonds, the atoms are still closer. Therefore, bond length is the strength of the bond increases as the bond order increases, and hence the distance between the nuclei decreases. So, we find that the bond length of a double bond oxygen should be 121 picometers, and if it was a single bond, it should be 148 picometers. But when you carry out the study of a molecule of ozone, we find that both the bonds of the 2 oxygens are 128 picometers. If they are 128 picometers, 128 is neither a single bond length nor is it a double bond length. It is somewhere between the two. It means that in ozone, the actual molecule of ozone is neither one of these 2 structures. It is neither one of these 2, but it is somewhere between these 2. Right? It's neither this nor that. So how would you imagine this structure to be like? I would say, look at your 2 palms. The thumb of this is on my left, right? And the thumb of this hand is on my right. Imagine these are the 2 Lewis structures. The double bond here is on the left and the double bond here is on the right. If I imagine this final structure to be, these are Lewis structures, we call them the canonical forms. These are the Lewis structures that you could draw. But the actual molecule, I would like you to imagine to be somewhat a hybrid of these 2. It is somewhat like it is superimposed and both of them, and now I have the double bond on the left, right and the left, both. So the double bond, now in this structure I am seeing both the double bonds, which are not proper double bonds, because if it was alone then it was a proper double bond. When I have the second structure here, this double bond is only for half the structure and this double bond is only for half the structure. So you can imagine this has a partial double bond character on the left and partial double bond character on the right. So that is what happened with ozone. The 2 bonds is like the double bonds are, it is like you have overlapped the 2 canonical forms, and the canonical forms have resulted in a resonance hybrid, and the hybrid is the actual structure. So the bond length, which was supposed to be 148 if it was a single bond, is now 128, and if it was 121, it is now again 128. Both of them are identical because some double bond character of this structure is seen here and some single bond character of this structure is seen here. On the whole, it becomes, the hybrid is a synthesis of all the canonical forms. Some other examples of resonance that you see in is this molecule. You see carbon dioxide. Carbon dioxide can also be described in 3 different structures. The way that we represent canonical forms is that we show a double-faced arrow. An arrow with 2 heads pointing to both the sides represents the canonical forms, and the hybrid, for the hybrid we use a triple line. So the resonance hybrid is shown by a triple line, while this arrow pointing both ways shows you the canonical forms. So carbon dioxide is seen to have 2 double bonds between the 2 carbon atoms, and these 2 forms are where with 1 carbon atom it has a triple bond and with 1 it has a single bond. So the resonance hybrid here would show what? It would show double bond length, it would show triple bond length, and it would show single bond length. It would be neither of these 3. It would be a hybrid of all these 3 if you superimpose these structures. So this is carbon dioxide. I've taken a third example here, that is the carbonate ion. In the carbonate ion, carbon is in the middle and the 3 oxygens, it's a planar structure, the 3 oxygens occupy the 3 corners of a regular triangle. And what do we see? One of the oxygens has a double bond and the other 2 have single bonds according to the Lewis structures, which we have already learned how to make. In another canonical form, the double bond is on this oxygen, and in the third canonical form, the double bond is on the third oxygen. So what would the resonance hybrid be like? Superimpose all 3 structures. So the resonance hybrid looks like this, where you have a double bond character on all the 3 oxygens. All the 3 CO bonds will show the double bond character. And earlier, in the canonical forms, we could show that each oxygen that has a single bond has the negative charge. And the one that has the double bond does not have a negative charge. So in the carbonate ion, the 2 negative charges are placed on the 2 oxygens which are bound by single bonds. But in the resonance hybrid, since all the 3 bonds are identical, it is not possible to specify which oxygens have the negative charge. So we put a bracket around the whole structure and give it a 2 negative, that the negative charge, there are 2 negative charges and 2 extra electrons in this entire structure, and you would just put it outside the bracket because you will not specify the oxygen to which the negative charge, where the negative charge is centered. So these were the canonical forms and the resonance hybrid of the carbonate ion. One more resonance molecule that you will commonly study in organic chemistry is benzene. Benzene is a molecule which is cyclic 6 carbon molecule. 1, 2, 3, 4, 5 and 6, right? And it has alternate double bonds, 1, 2 and 3. Every carbon forms 4 bonds, therefore how many bonds are already formed? 3. So every carbon has 1 hydrogen here, right? So this is a structure of benzene. Now each carbon forms 1 bond with the hydrogen and 2 bonds with 1 carbon on one side and 1 bond with 1 carbon on the other side. This structure is usually condensed and we make a smaller structure, and I'll just show you how that looks. And we draw their canonical forms. If you assume that, okay, we just make this structural formula. Each corner of the hexagon is a carbon atom, and we assume that the student already knows the number of hydrogens and all we are concerned about is the bonds. So in this structure, the double bond was here, here and here, right? In the next canonical form, the double bond, instead of being here, is here, here, here and here, right? So what did we see? In one canonical form, the benzene ring had the double bonds. Let us say this is carbon 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. We see an absolute shift of the double bonds in the second structure. Since they are alternating double bonds, in the first structure, the double bonds are between carbon 2 and 3, 4 and 5, and 6 and 1. But in the second structure, the double bonds are between 1, 2, 3, 4, and 5, 6. So all you see is a shift in the double bonds. So these two canonical forms, if you draw a resonance hybrid of these, we get benzene with a dotted circle in between. And the dotted circle shows the double bonds, alternating double bonds, and we show it as a ring here. The reason being that these double bonds are alternating between these 6 bonds. And this is the resonance hybrid of benzene. So this was the 5th bond parameter, that is resonance. Now in the next video we are going to study about the polarity of bonds. If you found this video helpful, please give it a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching. Bye bye.